like to welcome you all to Keeping Current today. Thanks for coming. I'm going to do the introduction this afternoon. Normally, Dr. Rafi Finkel, who runs the seminar, would kick off the seminar. He's given me license to do the introduction. So what you're going to hear today is the entire hour taken up by members of my research team. We're talking about what you may have seen recently in the news, virtual unwrapping. It's our effort at reading ancient scrolls using non-invasive techniques. And in the spirit of keeping current, what we'd like to talk about with you today is not what you can read in the press or in our technical work, but what you can only hear in keeping current. So you're going to hear about the current work that we're doing, why we think it's interesting, and what we think we can do. So without further ado, I'll introduce Seth Parker, who is our technical lead, and he'll take it from there.
So yes, you will be hearing from our entire research team today, with a few exceptions of people who have class and who can be here today. So yes, we are going to be talking about what we are working on, but to sort of give you a context for that work, it's important to know what we have done thus far if you have not been familiar with our work. So really, to get started, you need to go back to the 90s and the effort called the Digital Library. In the 90s, the idea was there are all these books in libraries around the world, and you want to photograph them in the highest resolution possible and make those photographs available online. And so you would do something like this. This is a multispectral imaging system, which basically you photograph an image of a page under a very specific wavelength of light, in this case ultraviolet, and you actually capture that image under multiple wavelengths, specific wavelengths, and that combination of images you can use to make full color, or you can use infrared to sort of bring out text and inks that have faded. So this was a really big thing in the 90s and leading into the early 2000s, and Dr. Seals, our fearless leader, was of course working in this realm. I love this. Oh no! There's something down here I shouldn't kick. I love this photo just because look at it. So I made sure to include it. But in the 90s, Dr. Seals was working in this area, and he was going to all these libraries and seeing all these awesome things, including things that you don't normally see in a library, and that was damaged materials. So it's great to say, yeah, we're going to photograph all the world's books, but how do you photograph something that you can't photograph without completely destroying the book? So this got us thinking about how do you deal with damage for preservation? And specifically, central to this question were the Herculaneum scrolls. Now, if you're not familiar with the Herculaneum scrolls, Herculaneum was a villa and library, well, it was an actual town near Pompeii when Vesuvius erupted, and it was covered in the same way that Pompeii was erupted. And there was a villa with a library of scrolls in Herculaneum. And all of the scrolls, similar to the way that all of the people in Pompeii were sort of perfectly preserved in some destructive way, the scrolls are sort of in the same state. They're sort of perfectly preserved inside, but you can't open them without completely destroying them because they're carbonized. They've just been turned straight to carbon. Now, people have tried to physically open them. This is a machine called the Piaggio machine, and the results were spectacular. And that is what you would get when you use the Piaggio machine. It would just try to slowly peel apart the scroll as if you were physically opening it, but as you can tell, extremely destructive. Layers would stick together if you tried to do something like that, and it would just totally destroy the actual value of the scroll. So you want to avoid this sort of damage. And this is what we talk about when we say non-invasive unwrapping, recovery, that sort of thing, is you want to recover all of the information from inside of the scroll without having to resort to this sort of thing. So that led us to virtual unwrapping. And this is a software pipeline that we've been working on for about a decade, really intensely in the last 3 years. We're entering into the third year of an NSF grant, the third and final year of an NSF grant to develop software along this type. And as part of that, we have this software pipeline that we've sort of focused on. So acquisition is just imaging the scroll. For that, we use CT scans. And then we follow this computational pipeline all the way down to producing images that textual scholars can do scholarship on. So as an example, I'm going to step you through the steps of this pipeline, and then this is going to inform what everyone else has sort of been working on through this. So this is a manuscript that we imaged in France in this past January. And as you can tell, it is extremely damaged. It's a medieval manuscript. There is clearly text on it, and this was destroyed during World War II. It was in a library that was bombed and then immediately doused with water to put the fire out, and so there is both fire damage and water damage in this manuscript. And you can just see when you look at it in profile how contorted all the layers and things are in there. So you put something like this into a CT scanner. This is a CT scanner that we used for Herculaneum scrolls. And what you get out of it are these cross-sectional images, a whole series of these. And this is basically, if you took that book and put it on its side and chopped the end off, that's what it would look like, sort of all the way through. And you'll notice these really bright spots through. That is actually ink, really metallic ink, that have absorbed a bunch of x-rays and show up really brightly in the CT scan. CT scans, this is a micro CT scan, so every pixel in this image is 54 microns in size. But it's the same technology as what you use when you go to the doctor. It's just the scale is a lot more fine. It's a lot, the resolution is much higher. So if we just rendered this data set, you can actually see words floating inside of this data set. So there's definitely text there, and it's definitely readable, but what word comes after which other word? That's sort of the orientation problem. It's just a bunch of floating letters. It's alphabet soup. So our pipeline tries to solve that. Segmentation, we create a geometric representation of a layer, and I'm simplifying a bunch of this stuff because it doesn't really matter for what other people are talking about, but basically we want to identify a layer and ignore ink, forget about ink for a second, and only find the shape of the layers inside of this manuscript or this scroll or whatever. So that's what we're doing here. We're sort of tracing the shape of the layer. And what you get out of it is this nice three-dimensional mesh that is the contour of that layer. Then, after you have that contour, you sort of have localized where ink should be. You know that ink's not going to be too far away from a layer, so what we do is we search really close in an area around that surface, and we try to classify that area according to what we think the ink should be. In this case, the ink, as you've seen, is really bright. It shows up really brightly, so it's a very simple search. Find the brightest thing in the area, and put that on the surface, and you get this. But this is a really distorted contour. You can't read it, and the ultimate goal of this is you want to read text. So we also have a flattening step that takes that 3D shape, maps it flat, and all of that texturing information that's there gets mapped flat as well. So now you have a readable word, which I'm told is Latin. I don't read Latin. If someone reads Latin, please translate it. But that's the basics of the pipeline. Segment, find the layers, add texturing to the surface, and then flatten that surface so you can read it. And we've had some really great results. Let me introduce you to the En-Gedi scroll, and I just realized I left my replica in my office. If someone who has access to our office can go get it, it's on my desk. We have replicas of all of these things that we've scanned. This is the En-Gedi scroll, and when you see the replica, this will be a little bit more impressive, I think. But we CT scanned the scroll, and these are the cross-sectional images, all the CT information. And this is an animal skin scroll. So the layers are a little bit more thick than some of the other data sets that we deal with that you will be seeing later on. But there's not obviously any ink in here, and it's really distorted. Here on the far right, you can see some of the damage that's happened to this scroll. But we performed our virtual unwrapping pipeline on this, and we revealed a full unwrapping with Hebrew characters, Hebrew text, which actually has been translated to be the book of Leviticus. And according to carbon dating, we can say that this is the oldest extant copy outside of the Dead Sea Scrolls for the book of Leviticus. It's about 1st, 2nd century. So really big. This was a paper that we released about a month ago now. Oh, do you have that? And so for scale, this is a scale replica of that scroll. So we were able to pull out from this, you can call it what you want. You think you know what the shape looks kind of like. But we were able to pull out of this all of that text, and at 1500 dpi, which we consider archival quality if you're talking about photographs. So really, really high resolution, all from something this big. And a text of a quality that we were able to do textual scholarship, paleography on this text. So we are really, really excited because this sort of proves what we're doing is valuable, but there are still the questions of Herculaneum scrolls. So we did CT scan some Herculaneum scrolls, and that leads us to the questions that we still have remaining unanswered. If we can unwrap these scrolls, then why haven't we solved Herculaneum? Well, when you scan a Herculaneum scroll, you see it's a little bit more complicated than everything you've seen thus far. And really, when you get close to it, it's even more complicated. There's just so many layers, and it's so contorted. It's just a problem on a totally different scale. So that's what we're trying to solve now. And also Herculaneum scrolls that we mentioned, we don't know what the ink looks like in CT scans. It's not metallic. It doesn't just show up really brightly. So we don't have that nice, easy classification problem for finding ink. And that's some of the things we're working on. So let me give you an outline of who you're going to be hearing from. Next, we're going to be hearing from Hannah and Michael. They've been working on taking our research project and getting it prepared for an open source release. At the end of our NSF grant, we're going to release this project to the community at large, and we want to make sure our code is not research code. It's actually something we can be proud of. So that's what they're going to be talking about, that effort. And Zach is going to be talking about something that actually is a little bit of a step back, but still related to Herculaneum. How do we want to take multispectral images and enhance what we know about those multispectral images by adding a three-dimensional aspect to them. And he'll talk about why that is. Then we're also, sort of for the CT scanning part, we're going to be talking about machine learning. How can we apply machine learning to both surface segmentation and also ink identification? And Kendall and Jack will be talking about each of those things individually. So without further ado, Hannah.
Good afternoon. As Seth said, my name is Hannah Hatch. I'm a junior here at the university, and I've been on the project for almost 6 months at this point. So, like he said, I'm going to talk to you guys about going open source. There are multiple challenges with going open source, one of which is making sure all of our code is up to standards. So, as Seth said, a lot of this has been going on since the 90s. C standards have changed since then. So, right now, our current goal for release is getting up to C11 standards. But if we're really optimistic, then we'll hopefully get up to C++14 standards, but kind of just depends on how the flow of everything goes. If you're not familiar with those standards, up here I have a good resource on finding those out. Some of the things that we're doing include making our functions const correctness. So what we're doing is if a function only returns a value from say a member of a class, then we're making sure it's a const function so that all of the data stays the same. You're getting what you expect, and you're not going to get something funky. Another thing we're doing is we've implemented tools to help developers maintain good code. So one example of this is our Clang format. So on the left here, you can see there's all of that extra white space. It doesn't really make any sense as to why that's supposed to look like that. We run it through Clang format, and on the right, all of that extra white space is gone, and it looks more uniform. It can't help with the naming of variables, but it can at least help make the code look more readable. Another thing we're doing is we are implementing a testing system. So what you see up here is, this is what our code goes through whenever you push a commit through Git, which is what we're using to help create a good workflow. So first, it builds on the two systems that we support, Debian and OS X. After that, it runs a list of tests. So the first one up here, that lint, that's that Clang format I just discussed. The other two are a set of tests that we have created to test each part of our code. So the segmentation, the texturing, everything gets a test so that we know what's working. If you write a new piece of code, if you write a new application, you add a test for it. That way, if you run your code and if something breaks, we know which part is broken and how to fix it. Another important aspect of going from a research project to an open source project is proper documentation. So up here is an example of Doxygen documentation. This is good code documentation. On the left is what you would add in for your code. So all it is just simply adding in extra commands as you're writing your code documentation. But what comes out is what you see there on the right, which is a good readable format. So a developer can go on, or maybe a user can go on and they can see what each of these functions are doing, what they take, and what they return. It just helps make it easier, make the transition from a research project to an open source project easier. No longer are the developers going to be just upstairs or coming in later this week. They're going to be developers from all around the country and all around the world, so we want to make sure that they can understand what we're doing. And part of that also is having good build documentation. A developer who doesn't know how to build our project isn't going to want to work on it. They don't want to put in the extra effort to figure out how to do it when there should already be good documentation on how to build it. And lastly, we want to have good contribution documentation, meaning we want to make it easy for people to add to our code. Part of that is having a good workflow, which we do through Git. So when do you open an issue? When do you branch off? When do you open a merge request? Good contribution documentation will tell the developer exactly how to do that, and so that's really important. You also want to clean up the code base, because you never know what's lurking under there. I'll explain more what that means in a minute. But first off, how do you do this? So first off, you want to remove code that you aren't using. All it's doing is it's increasing build times and it's making things a little more complex. A developer sees a function and they go, well, I don't know what this is doing, why is it here? If it doesn't need to be there, it shouldn't be there. Another thing we're doing is we are removing dependencies that have minimal usage. So most recently, we removed a library from our code because we weren't using it that often, and instead we replaced it with something that we built ourselves. Part of this goes with the next point on there, which is for licensing. So part of going open source is getting an open source license. What we're looking for is something that is the least restrictive, but also fits in with all of our external code. So by removing these minimally used dependencies, that's one less license we have to worry about when we go out to get our open source license. So I mentioned before, you want to find what's lurking in your code base. Here's an example of this. This is code that was actually in our project at one point. It's no longer in there, I promise, but it was in there at one point. So besides the obvious, why is this bad? As a user, if you get this error message, you don't know where it's coming from, you don't know why you got this message. You can't give a lot of information if you submit an issue or if you're trying to talk to a developer. As a developer, you don't know what this wants. What arguments do I need? How many do I need? It makes it harder. You have to go through the code to figure out what it wants. So here's a good example of that. So as compared, you have a list of arguments here. You can see what does it want, how many does it want. As a user, if you're getting this error, you can go to a developer, you can say, hey, I'm getting this error, here's some more information, and it makes it easier for them to help you. A slightly less funny example, a little more serious, this was a very simple, basic change we made. And part of this was to help with make it easier to understand and for a more concise and clear naming system. You see where it says VC point type, that gets changed to ITK, so that way you know you're working with an ITK mesh, ITK points, and you have you can have a better understanding of what you're working with. So when moving from a research project to an open source project, you have to keep in mind, your code needs to be up to standard, it needs to be properly documented, and you have to watch out for crazy little things like that. Up next, you'll have Michael talking about improving your user experience.
Hello, I'm Michael, and I'll be talking about your user experience today. So when we first started, we began as a research project. Essentially, we were doing scans, trying to understand the pipeline and what the direction of the project was going to be. We didn't know what we were going to need or what applications we were going to write for the user experience. At the beginning, it was mostly command line and just trying to figure it out. But as we got further into it, we realized we needed applications that allowed users to segment the scrolls and also to do texturing. So as you can see up there, Qt, that's a graphics library that we use, and CLion on the right, that's a text editor. Those applications allow us to write the two applications that we have now, the VC texture and the VC application. What's most important is our users. we have scientists and scholars who are going to be using these applications in order to unwrap the scrolls and then share it with their colleagues. On the left, you can see the volume cartographer. It began with a colleague of mine before my time, and since then I've worked on it to improve it. And we also have the VC texture, which I wrote in order to do texturing and used our pipeline in order to give users the ability to create texture images, export, and share them. We're able to load a volume package. Now, a volume package is a type of 3D sort of volume type that we created. And essentially that allows us to go through and take the data that we want. And with the volume cartographer, we can go through the segmentations and sort of draw the path that you can imagine on the scroll. And then go layer by layer into that scroll and see what we want to keep or we want to change that segmentation. Once we have a segmentation, on the right with VC texture, we can load those segmentations into VC texture and then use our different formatting techniques in order to texture the image and then get something that you're able to read. Now there are some good and some bad things about the way it's been set up. The good is that we've been able to do fast implementation of the user interfaces. There's currently 2 user interfaces. We might add 1 more. We're considering to get the functionality. Now, what's also important to remember is that although we have these user interfaces, these 2 separate tools, it fails to clarify certain requirements. As we get more functionality, we can't continue to create more user interfaces essentially, which is one of the things that we need to talk about. But what's good is that we're able to get the concept and we're able to do the specific tasks. So for segmentations, we're able to find the segmentations and improve those specifically with the VC applications, VC app, and VC texture. We're able to work on our texturing. Now, this is the most important part of my presentation, is what we can improve on. Currently, there are 2 applications, the VC applications and the VC texturing. It's been good for now, but as we continue, we're going to have users who are scholars, and we're going to have users who are benchmark scientists. They're not going to know the full functionality of our code. They're not going to know how to write certain functions and do command line. They need something that's easy to use, that anybody can use and pick up and figure out, how do I unwrap the scroll? So what we're going to do is take the application for VC app, VC texture, registration, neural networks, machine learning, and put that all into one user interface. So you won't be loading 3 or 4 interfaces and saying, hey, am I here, am I here, am I here? It'll be one interface. You can check for different functionalities. And because we're expanding our code base and expanding our functionalities with neural networks and machine learning to find the ink on the page and all this, we need it to be scalable. Right now, if I wanted to add that functionality into, say, the texture app, honestly, it would be a big hassle because I'd have to go back and change a lot of things just in order to get it to load and do what I wanted to do. Because doing neural networks is entirely different than doing a texturing or segmentation. To put this in perspective, whenever you say you want to do something at your home or something like that, you have a certain task, you go for a certain tool. But you might keep it all in the same closet. That's essentially what we're doing with the new user interface. You're going to have one closet with all your tools. You want to go wash the dishes, you can get your soap out of there. So with this one closet, this one application suite, you're going to have everything you need under one development environment, which is also good for our developers. Our developers are going to be looking at our code, trying to understand how do we scale this up for new functionality. Because there might be new functionality in order to unwrap the scrolls that we haven't even thought of. There might be a potential to, say, do it in the 3D environment with virtual imaging machines in the future. And what's important is that we have the code base and the scalability to implement that as we go. Because as the future keeps going, we're not sure where it might go. And also what's important, right now we only are able to run it on Mac and Linux, which puts a disparity on Windows users, and I'm one of those users. So I'd like to see our functionality fully working for all 3 operating systems, Mac, Linux, and Windows. And what's most important, especially to me, is our users. We have scientists and we have scholars. I've experienced in the past as a developer, I might create something that I think is going to be good for you. But until I actually have you test it and see how it feels to be the user, I won't fully understand if what I wrote is good enough for you, and I need to make changes. So incremental changes and being able to give our unified application suite to the actual scholars to test it out and say, hey, I really like this, but I think this can be improved. I'm a little confused here. That sort of unique testing is going to help us so that when we go and make this open source, that we're going to have a lot of people willing to give us feedback and to continue to improve. But those are the most important things: scalability and user testing. The next person up is going to be Zach, talking about 3D enhanced spectral imagery. Thank you.
Hello everyone, my name is Zach, and today I'm going to be talking about 3D enhanced spectral imagery. What that essentially means is mapping a 2D image to a 3D plane. What's really interesting about this is that we've actually done a lot of mapping in the past. In fact, we've already developed a framework for mapping an image to another image. This is formally actually called the Registration Toolkit. So when Dr. Shields and Seth went to Oxford, they actually took images of this Herculaneum fragment. So we officially now have 3 different versions. We have a 1998 version, a 2005 image, and a 2016 version. So my first task was to take all 3 of those images, run it through our framework, and then be able to put it into a viewer so that way someone can go online and be able to compare and contrast the images. So I've got a little demo here of that. So this is the, let's see. Oh, there it is. Oh, it's already up there. Okay, so just to kind of go through it, what you have is you have one version, which the outside version is the 1998 version, and then you actually have this little flashlight, which is kind of cool, and this is the 2016 version. So each one of these 3 different versions are here, and what you can do is you can actually move this flashlight around and be able to compare the 2016 version with the 1998 version on the background. So as you can see, they're aligned. So we ran it through this framework, and you're able to essentially move through different images. So let's see. So now this is the 2005 version that is inside of the flashlight, and so you can compare and contrast like that. So that was my first task that I had to do, was just to run it through that framework and be able to have them aligned. So now let's talk about 3D. So how many of you all actually know what a 3-dimensional object is? Just show of raise hands. Okay, cool. So this was actually one of the first things that I didn't really know about. We always talk about 3-dimensional objects in like math and stuff like that, but we don't actually really talk about it that much in computer science. I knew obviously that a 3-dimensional object has 3 dimensions: an x-axis, a y-axis, and a z-axis. But what I didn't realize is that a 3-dimensional object, which is also called a mesh, is just a bunch of points combined together. And then what you do is you take an image and just wrap it around those points. So what you can see over here with this visual representation of a duck is that duck on the left-hand side, that's the mesh representation. But then on the right-hand side, it's just taking an image and then putting it over top of those points. So I thought that was kind of interesting. So why are we dealing with 3D? Well, for the fragments, it's actually very hard to visually see layers stuck together in 2 dimensions. So that's why 3D is really important here. So when Dr. Shields and Seth were in Oxford, they also acquired 3D data. So that was really neat, and here is actually a demo, or just a video of the 3-dimensional data. So as you can see, the 3-dimensional data has a bunch of points. This is the mesh. And you can actually see, the bumps and things like that. You're able to see the different layers. Even that, you also have a texture. So this is what the texture, the image looks like over top of the points. So that's really cool. So now what you might be asking is so if you have a 2D image, why not just use the existing framework to be able to map a high resolution image to this three-dimensional object? Well, here's the problem is that this is the image that we want to use on top of the three-dimensional object. But this is the actual texture image on the right-hand side. So there's no way to actually physically be able to map that. So as you can see, because of the way that it's mapped, we have to figure out some way to be able to figure out where each part of that image goes. So there's a process. At the highest level, I kind of broke it up into two parts. The first part is the mesh alignment. So we want to essentially just get rid of the z-axis. So when we're messing with the mesh, we have to rotate it and translate it to make it just be on an X and Y plane. Then once we go from there, we can then plug it into our existing two-dimensional framework and be able to figure out the mapping with the texture images. So here's just some results that I have so far. What you can see on the left-hand side is what we originally have as far as the mesh is concerned. And then on the right side, we've taken away the z-axis. So this is after the rotation and the translation. And you actually can see it a little bit better on the next slide. So here was angled, and now we have it perfectly flat. So it makes the job a lot easier to be able to go